Hi, I'm Christian and today I represent a research group from the University of Zagreb. The title of our paper is Generalizable Human Pose Triangulation. The task that we are concerned with is the 3D human pose estimation from multiple views. One of the main limitations of the previous methods is that they cannot be used on the dataset or even camera arrangement different from the arrangement of the training data, or their performance is significantly degraded. This is very limiting in practice. We propose a learning strategy that makes our model invariant to the camera arrangement, the number of views, and dataset. Based on a single multi-view frame, we generate a pool of a few hundred hypotheses. The hypotheses are passed through a simple MLP to estimate the score of each hypothesis. This is the only learnable part of our model. The final estimate is a weighted average of the hypotheses. The hypothesis generation and the final estimation strategy is a form of soft differentiable rancing, previously proposed in the literature. A single pose hypothesis is created by selecting a subset of views for each detected key point. The 3D location of the joint is triangulated using the selected subset of views. By generating many combinations, the model has a choice of selecting the most probable hypothesis. The key insight is that the 3D pose hypotheses scored by the MLP are normalized in order to achieve invariance to the camera arrangement. The poses are normalized in a way that they are always oriented in the direction of positive y-axis. The unnormalized poses are then used to produce the final 3D estimate. The disadvantage of the first pose normalization strategy is that it might combine 3D poses with various orientations due to invariance of the scoring function. A simpler but more successful normalization strategy was to extract the body lengths. It turns out that only body lengths are sufficient to differentiate between the good and bad poses, which we will show in the experiments. This is an overview of our method. We use a single frame 2D key point detections from multiple views to generate a pool of normalized 3D pose hypotheses. The 3D poses are scored using an MLP, and the final estimate is a weighted combination. The loss is calculated using a standard mean per joint precision error. The first table demonstrates that our model achieves consistent performance regardless of the camera arrangement, number of cameras, and dataset. The last column indicates that the intra-dataset performance difference is up to 4.4%, while the inter-dataset difference is somewhat larger. Compared to Remeli, the intra-dataset performance difference is significantly smaller. The volumetric approach by Iskakov demonstrates generalization between the Panoptic Studio and human 3.6M datasets. We outperformed their model by 8.8%. Compared to the most successful voxel pose model, we achieve only slightly better result on the Panoptic Studio dataset. However, we did not retrain our 2D backbone on Panoptic Studio, which might improve our performance in the future. In the qualitative evaluation, we showed that our model differentiates between the pose hypotheses, namely the most and least probable one, with respect to the given scores, and compare them to the weighted hypothesis. The difference can be seen even better with respect to the human pose prior metric, which measures the consistency of the body length ratios over time for a single person. The consistency of our weighted hypotheses are even more consistent than the objectively best hypothesis. The biggest limitation of our model is that it heavily depends on the performance of 2D pose detector, which can be mitigated by end-to-end learning. The biggest advantage is that it can be transferred to datasets different than training. Thank you for your attention.